So today I will present you the work we have done so far on my PhD project, optimization of maritime zero-emission transport systems. I will start very quickly with the motivation, what's behind the project. The CO2 emissions must be decreased by 40% towards 2030. And the maritime sector is an important contributor to the emissions from the transport sector. So when we manage to introduce hydrogen as a fuel in the maritime sector, we can reduce the CO2 emissions significantly. And the main question in our PhD project is how to design the hydrogen supply chain for maritime transportation in Norway. Now let's have a look at the question a little bit more in detail. We have two groups of research questions. The first group is more related to the application, to the real design of the supply chain, while the second group is more related to the problem, which solution method to use. So I will start with the first group of questions. So first of all, we have to decide whether we will go for local production in most of the selected ports or for large-scale production in few ports and following distribution. It's also connected with the decision which capacity and production technology to install, because we can choose electrolysis, which is more favorable for small quantities and small-scale production, or steam methane reforming with carbon capture, which is more relevant for large quantities. We also take assumption in our first two papers, and it's a simplification where we assume that we can install steam methane reforming at all locations. And then we also have to decide which period to choose for investment and expansion. And finally, it will be mostly the part of our future work. How does uncertainty in demand affect the structure of the solution? And also having in mind this last question, the question related to the solution method becomes more relevant because we have a large mixed integer problem, and it's hard to solve it with commercial software. And for some instances, for some large instances, the commercial software can't provide any feasible solution. So we have to think about which solution method to use, considering the structure of our problem, and then also how to implement it. Because what we need to achieve is that we need to solve large models, and we need to solve them in some reasonable time. And also, we want to solve them for more scenarios in the stochastic setting then. Now a little bit about our modeling approach. We have a multi-period facility location problem with capacity expansion, and we allow the opening and expansion at any time during the planning horizon. However, the expansion is allowed only once during the planning horizon because it's quite expensive, and also the planning horizon isn't so long so that we would expand every second period, for example. And then once the facility is opened, we can't close it anymore. We will keep it for the whole planning horizon. We consider modular capacities, but we allow the production quantities to vary from the installed capacity, in the sense that we allow to produce less than the installed capacity is. But we have also limits on production quantities, lower limits. In our model, we separate investment and expansion costs as long-term costs from the production and distribution costs that represent the short-term costs. And finally, we introduce restrictions which facility can satisfy which customers. So if the distance between facility and customer is too long, we can't establish this connection. And now very quickly about how we model our expansion. So at the beginning, we can open a facility with a small capacity, and then we pay these investment costs. And for this small capacity, this short-term production cost function is available. And you can see that we can produce less than we installed. But at the same time, higher utilization leads to lower unit costs. And then when we decide for expansion, we jump to the higher capacity, and the expansion costs consist of the investments cost into the bigger facility minus the investments cost into the smaller facility we have originally opened, plus some markup, because we model expansion as a more expensive alternative than opening a bigger facility right away. And after expansion, this short-term cost function becomes available. And this is the same no matter how we reached this capacity. And now to our case. we consider 17 candidate locations for hydrogen production facilities on Norwegian west coast. These candidate locations were provided by Ocean Highway Cluster. Then we also assume two hydrogen production technologies, electrolysis and steam methane reforming. And for electrolysis, the production rate can vary between 20 and 100%. So it's also where the requirements on minimum production quantities comes from. We have also distance limit between the production facility and customer. We have set it on 1,000 kilometers. And now to our demand scenarios. The basic scenario is maritime demand. The underlying assumption is that we assume the same level of services as for now and no changes in the ferry routes. And this is this blue line. It's moderately increasing in the first 10 periods, and then this jump in period 11 is the coastal road Bergen-Kirkenes, when it's supposed to start operate on hydrogen fuels. Then the other scenario is all transportation demand, which is the maritime demand plus road traffic on the top. And this road traffic demand is based on the estimations in the DNV report from 2019, where hydrogen is alternative for long distance buses and heavy duty trucks. And now we can, I will show you our objective. We have a minimization problem. So the goal is to minimize investment costs, expansion costs, transportation costs, and production costs while satisfying demand in each period. And now we can move to our first result. So the figure on the left-hand side shows the infrastructure, the locations with open facilities and their capacities for maritime demand, and the right figure shows the infrastructure for all transportation demand. The common feature is that we, in both scenarios, open only electrolysis facilities. The reason is that our demand is quite low, and we also can't close facilities. So then later, when demand is finally large enough, so that it would be reasonable to consider steam methane reforming, we already have some facilities that must be operated at least 20%, and we can't close them. So the remaining demand is not large enough to justify a steam methane reforming. But now when we compare these two figures, there is nothing special in the northern part of Norway, because the demand in the northern part of Norway comes mostly from the maritime sector. So there are no big differences. The biggest differences are in the south, because most of the road traffic demand is located in the southern part of Norway. So in general, we open more facilities or larger facilities here on the west coast. But the biggest difference is here the facility in Slemmestad, because this facility is supposed to cover most of the road traffic demand located in the Oslo area. Yeah. But also, when if you have a look at these two figures, the number of open facilities is approximately the same. And it will be important also when we come further. But what we have learned at this during when we studied this, when we work on this first paper, is that the problem is hard to solve. It takes about 3 hours to get the result when we use cluster. And for larger instances, we can't get any results from the commercial software. So we need a solution method that can provide good solutions within fast run times. And that's what our second paper about. It's the Lagrangian relaxation for the multi-period facility location and capacity expansion. Here is our mathematical model. I won't go through it equation by equation. It's just the important one is here our demand. Is here this requirement that all demand must be satisfied. And after we relax this constraint, the nice feature is that all other constraints are defined for each facility location. So then the problem can be separated in facility locations, and we can compute the problem independently for each facility location. So it's much easier to solve. It also enables parallelization, and we are much faster then. The objective single facility problem is very similar to the previous one. We just have to work with reduced transportation costs. And then in order to get the lower bound, we make a sum over all facilities and add the Lagrangian penalty term, which is independent on facility location. And now how to solve the relax problem, because we want to avoid using the commercial software because it's slowly. So in order to find the optimal solution for the relax problem, we need to find the optimal opening and expansion schedule. It means optimal opening and expansion time and capacities. We can formulate the problem as a shortest path problem and solve it with efficient dynamic programming algorithm. So here is a small example for 3 capacities and 5 time periods. And why it's, so to say, so complicated, because we still need to have in mind that we are allowed to expand only once during the planning horizon. So first of all, we have to define target capacity. That are these black boxes. And it's the capacity we want to achieve at the end of the planning horizon. And then for each target capacity, we define a subgraph. And you can see that these subgraphs are almost independent. They are just connected with the artificial source and target. And in each of these subgraphs, maximum 2 arrows up are allowed, which means maximum 2 capacity changes. First of all, when we open a facility from the 0 capacity, and for the second time when we expand. But the expansion must go directly to the target capacity. And then we pick up the best subgraph because it's the shortest path. And then we can also ensure that our shortest path is feasible for the is a feasible and optimal solution for the relax problem. Unfortunately, the solution of the relax problem is not feasible for our original problem. So we need a heuristic to build up a feasible solution. So we start with the solution from the Lagrangian subproblem, where we accept the locations and opening capacities of the facilities and also the utilization. And then we allocate demand to these capacities. But then the main question, our upper bound is driven by this question is all demand satisfied in all periods? Because if not, we need to expand capacity. We need to increase the capacity of the infrastructure. So what we can do first is increase utilization. If it's enough, we can just jump straight to the next period. If not, we can open new facilities, expand existing facilities, and in the worst case, if it doesn't work, we can expand capacity and ignore the requirements on minimum production quantities. And now I will just very quickly show you why this last step doesn't violate the feasibility of our solution. Because when we have to open a new facility and ignore the minimum production requirements, we are in a situation that here is our new facility, and all the facilities in the neighborhood are fully utilized, which means that the utilization is 100%, because otherwise we would use them to satisfy the demand. So what we can do in order to achieve the feasibility is to reallocate the customers from these neighborhood facilities, and then the utilization works for all facilities we have opened. Then in the next step, after we have enough capacity in all periods, we have to optimize capacity in the sense that we have to reduce capacity, because it's still possible that in this first step, when we solve the relax problem, we installed a way too much capacity. So now we can reduce it. And afterwards, we get a feasible solution. We can improve the solution a little bit as we use the Gurobi optimizer for solving LP, because we fix the facility locations and capacities and re-optimize only the distribution and utilization of facilities. And at the end, we get a nice feasible solution. How nice the solution is, I will show you in the result part. So our results, first of all, consist of comparison between Gurobi and our algorithm. So Gurobi is our benchmark. And we compare the runtime and gap, and also the quality of the feasible solution we have found, so the upper bound. We use parallelization, and it's fair because Gurobi does it as well. So if Gurobi has 32 threads available, it can use all of them. And now we can go to our first results. So the first two figures show the results for the problem with 17 facilities, 51 customers, and 8 capacities. It's the maritime problem I have shown you before. And here the blue lines show the lower bound and upper bound of our algorithm. The orange dashed lines show the upper bound and lower bound of Gurobi. The same colors applies here when we plot the gap. And the red line is the optimal value. So you can see that at the beginning, we are much better than Gurobi. We can find a good feasible solution very quickly. But then for this small problem, Gurobi can outperform our algorithm because after 200 seconds, Gurobi goes into the direction of optimal solution. But anyway, here you can see that the feasible solution we have found with our algorithm is very close to the optimal one. But now we come to the point where our algorithm has an advantage, and it's just a slightly bigger problem with 70 customers. But this 70 customers also comes with higher demand. And it's also the reason why a bigger problem is easier to solve with our algorithm than the small one. Because here you can see that for the bigger problem, we need only 44 seconds to achieve a gap lower than 1.5%, while for the smaller one, it's about 1 minute. And the reason is that higher demand means that it's easier to satisfy the minimum production requirements. And then the problem is easier to solve with our algorithm. But now when we compare our results with Gurobi, you can see again that our solution is very close to the optima. And here the advantage of our algorithm is much more visible. And also now when we have a look at gap, so after 300 seconds, we are already below 1%, while Gurobi is after 300 seconds still above 10%. And now the last comparison to show the advantage of our algorithm when the problem size increases. We have a comparison for 17, 34, and 51 facility locations, and for fixed 51 customers and 8 capacities. So here the blue line, it's the same problem as on the previous slide. We are better just at the beginning. But then when the problem size increases up to 51 facility locations, we can still find a nice solution with a gap lower than 1.5% within 98 seconds, while Gurobi needs more than 2 hours. And after 500 seconds, Gurobi is still way above 10%. And now a little bit to our future work, or what we are working on now. It's a stochastic model. It's a two-stage stochastic model where the first stage decisions are related to opening of new facilities, and the second stage decisions are related to expansion. And demand is uncertain. And what I can say by now is that the problem is basically impossible to solve for more than 10 scenarios with a commercial software. And even the 10 scenarios take about 5 days to get a solution with a gap about 2%. So we really need a solution method to be able to solve it with more scenarios. And also the expansion in the second stage provides a lot of flexibility. So then it's quite easy to react on growing demand if we have the option to expand in the second stage. But what we need in order to improve the solutions is a good solution method that can provide good solutions for more scenarios. And so far, it seems that it could be Lagrangian relaxation. We can relax the demand constraint, and then the problem is still separable in candidate locations. And then for the lower bound, even with the nested structure, we can still formulate it as a shortest path problem and solve with dynamic programming algorithm. The issue then is the upper bound to find a feasible solution, a heuristic how to build a feasible solution. And that's the future work then. Yeah, thank you for your attention.